All right, thank you. Okay, in this talk, I'm going, just a second, I need to get this a little bit. Okay, so in this talk, I'm going to present to you a little bit improved model for the for static transmit beamforming. So basically, the whole talk is trying to give an answer to a question, which is, can a simple geometric approximation of the focused transmit beam be used for synthetic transmit focusing? I'm gonna remove the suspense and say yes. Okay, so now you have the answer. But in the rest of the talk, I'm going to present what is the role of focused beams in synthetic transmit focusing. Then I'm going to discuss a little bit how adequate is the virtual source model. And then I'm going to introduce the new geometric model. It's not really new, but it's the one that we're using. Then I'm going to show how it is validated in simulations and measurements in phantom, and then in the end just an example in vivo how it actually works and performs. So for this audience, I'm trying to get here the pointer. That's the pointer, and this is again a pointer. All right. Okay. So for this audience, I don't think I have to say much, but all of you know that there are the keys to synthetic aperture is that if we want to focus in a given point, we have to insonify that point from different directions, and then we combine the different the data acquired to the different transmissions coherently, that is in phase. So here I'm showing three types of excitations, or three types of waveforms that are used. So starting from right to left, we have plane waves, we have focused transmit beams, and then we have defocused transmit beams. So what you're seeing here is basically what often is known in literature as a low resolution images. So in order to do the focusing, we can say that the signal in the final image at a given point y is a sum of the signals received by the transducer elements x, and this is a double sum, so it's a sum over all received elements, and it's a sum over the transmit events that contribute to the acquired data. In order to sum the signal coherently, we have to pick up the samples at the right time. So we have propagation time in receive, which typically would be from a point to a receive element. And then we have to take into account the propagation time in transmit, which is from the center of transmission to the given point. What you're seeing in these images here is the result of focusing without the transmit time, which is why you can see that the points, for example, here they fluctuate up and down. This is basically what typically corresponds to your propagation in transmit. So you can see that in the focused emission, you also have a change in the arrival time, which is what is going to give us the focusing based on the synthetic transmit focusing. Same thing applies for plane waves, because different directions of plane waves make it so that the wavefront arrives at a point at a different time, and the same thing applies also for diverging waves. The sum can actually be broken into two, so we can have, in the first step, we can create an image or beams which are only, in which we use only the receive beamforming. AR is the apodization, which typically maintains resolution in receive or being uniform, and then TR is the delay in receive. And then when we sum all these low resolution images, we can get the signal Y. AFT is basically the apodization with which we can weight this summation. So for example, if we take the focus transmit, we don't want to add any signal that is outside of the beam because we are not contributing with any signal, and what's going to happen is that we are going to ruin our beamforming process. Same thing applies also for the diverging waves, and although we don't see it, a similar condition exists for the plane waves. So basically, what I'm going to focus is on the calculation of this AFT. For many years, we have approximated the beam, which is the focus beam, using a virtual source. Basically, what we're saying is that when we focus in transmit, all the waves converge to a point, which is our focal point, and that is why we call it virtual source. And the time it takes for the wave to travel from the origin of transmission to the point at which we want to focus is basically the sum of the propagation time from origin to the virtual source. So this is the first term, and from the virtual source to the point in the image, which is the second term. If the point was here before the virtual source, then we would have a minus sign. Is this adequate? Well, many years ago, 15 years ago, those were the first results that have been done. This is some of our results. So what happens is that we have acquired data using focus transmission. In this particular case, the transmit focus is at 4 centimeters or 40 millimeters. And the same data have been used to create this image and this image. Here we have only dynamic receive focusing in this one. And here we have synthetic transmit focusing using a virtual source placed, using for a model of our wave propagation, a virtual source placed at the 40 millimeters. And as you can see, we can get a higher penetration and better signal-to-noise ratio as a function of depth. So this was an indication that this model works. And if we create a low resolution image where we have a focused beam with an F number of 1, we can see that actually the beam converges towards a point, and then it diverges. So this model works reasonably well for F numbers on the order of 1, 1.5. However, if we go to larger F numbers, the model breaks because we have this focal zone. So here you cannot really attribute anything to converging to a single point. And this is what we try to describe the shape of this beam. So you may ask, well, can't we just use focus transmissions with F number of 1? Because we cover a much larger region, we're going to get a much stronger or much more clear synthetic aperture effect. Yes, we could, but what kind of focusing we use depends on the application. If we have a strong transmit focus, this means that we have to have lots of transmissions because we cannot undersample our field at the focal point. So if we want to have faster imaging, then we have to use higher F number so that we can cover the whole region faster. And basically the model that can explain our beam with F1 cannot explain our beam with F number of 8. So this is basically the motivation for this work. We haven't invented anything. We just looked into literature, and we tried to see if a geometrical model developed 50 years ago or 100 years ago, I have no idea, for a concave transducer, circularly symmetric, if that can be used for array imaging. And that model basically divides the beam into the field into 3 zones: near Fresnel zone, focal zone, which they call it which is called Fraunhofer zone, and a far Fresnel zone. So each of these zones, the first step is to determine the start and the end depth of each of these zones. And I'm going to use the 3 points A, B, and C. Before we start determining the depths, we need to calculate a depth called ZS. And this is the depth at which the so-called Fresnel number becomes equals to 1. So so if this transducer would emit a plane wave, that is approximately the place where the plane wave will start diverging. This depth is equal to the size of the aperture squared divided by 4 times the wavelength. And in all the results here, the wavelength is assumed to be the center frequency of the transducer. The near Fresnel zone starts at the surface of the transducer, and it finishes at set B, which in literature is also known as the near transition depth. And ZB can be found using this simple expression, which is the focal depth ZF, so this is where we focus our transducer, times the Fresnel depth ZS, and then divided by the sum of these two. It is a well-known expression, there is nothing new here, but it is developed for a concave circularly symmetric transducer. And then the far Fresnel zone is everything beyond the depth ZC, which can be calculated as ZF times ZS divided by ZS minus ZF. I'm not going to derive this, just open your textbooks and see how it is. So this is where the different zones start, but it doesn't help us to calculate our beam shape. So the beam actually diverges slightly within the focal Fraunhofer zone. And the angle of divergence, alpha, it can be calculated as arc sinus or arc sine, lambda divided by d, and a coefficient A1. Now, again, for a concave circularly symmetric transducer, A1 is 0.61 or 1.22, depending if you take a radius or a diameter. For the case of an array, this actually is different. And then in the far field, so after we have found this diverging angle, we can just get the crossing points. And in the far field, we also have another angle diverging, beta, which is dependent on a different constant, B1, but otherwise it is the focusing depth divided by, so basically this is the F number. So what we have now is a model which is dependent only on the size of the aperture, the wavelength, and the focusing strength. And this is how the shape of the beam looks like typically. So in order to verify if this actually works, we have done some simulations using field 2. And we have simulated transducers which have elevation focus. They are based on real transducers, the simulations. And we have studied the wavefront to see what kind of models for the wave we can use in the near field and the far field. And one thing that actually pleasantly surprised us is that this simple geometric model captures very well the 3 dB intensity of our transmit beam. So we did this. So we did a simulation for one single transducer, just to figure out A and B, and then we repeated the simulation for a number of transducers. And we compared how the simple geometric model matches the 3 dB or 6 dB beam contour. So what we have here, this is the center line of our beam. This is just one-sided profile of our beam. The yellow line basically is the geometric model, and I don't know if you can see it, but the red line and the surface or the patch filled in with red, that is taken out from a field 2 simulation. So actually it's amazingly a good match. Then we did scans in a phantom because we are kind of lazy, so we didn't do it in a water bath. So we created such low resolution images like the ones that we have seen so far in a homogeneous phantom. The time gain compensation was set in such a way so that we get an uniform brightness of the speckle as a function of depth. We did some smoothing on the image to avoid artifacts from speckling. Then we have done some segmentation, and we have It can be seen that actually this approximation works also very well without any fiddling or tweaking. Also, for the same transducers that have been simulated, they also fit in reality. So we have used that model to do synthetic aperture imaging. In this particular case, it's a curved array. This is the data is acquired. It's not the same data, but it is acquired frame interleaved. So we have one frame normal focusing, one frame synthetic transmit focusing. The focal point is placed around 11 centimeters, actually 11 centimeters. So what you can see is that the quality of the two images is good in depth, but because we have a focal point at 11 centimeters, this means that the beam is quite broad, close to the transducer, which is why the resolution and the contrast in the near zone is not very good. But after applying the synthetic transmit focusing, we actually can enhance those structures. So to summarize, what we have shown is that a simple geometric beam approximation can be used for synthetic transmit focusing. The approximation divides the beam into 3 regions and depends only on the aperture size, focusing depth, and wavelength. And we have verified in simulation, phantom measurements, the model, and we have demonstrated in vivo that it is usable for synthetic transmit focusing. Thank you.